All right, so we shall look at the next slide. Which of course is a continuation from where we started from. I had done these records, but it seems I had lost them. They were not recorded well. So we had first looked at energy, we had looked at work, we had looked at power. So to just give you some brief outline on what we looked at last time, the first thing that we actually learned is that work for a non-constant force, it doesn't produce, of course, a straight line. Then we also looked at the spring force, which is F is equal to minus kx, where we said F is the applied force, the K is nothing but the spring constant, and the X is the distance that the body actually moves. Now, the potential energy of the spring, we defined it as half kx squared. And of course, the power we said is the rate at which work is done, which we say power is equal to change in work over change in time. So in other words, the power also can be defined as the force multiplied by the velocity. Now, coming to momentum and collisions, of course, some of these questions you've already tackled in the test that you had this week. So it's just to go through and remind you of the information that most of which you already know. Momentum, of course, would say is nothing but the product of the mass of an object multiplied by its velocity. In other words, what we are saying is that from second law of motion, we know that from definition, F is equal to ma. So the momentum, the change in velocity over the change in time, that is what gives you the momentum, whereby we are saying that actually F is defined as the change in momentum over the change in time. In other words, the change in momentum can be defined as F multiplied by the change in time. So let's look at conservation of momentum. In other words, when we talk about two particles that actually collide, so we'll first look at before collision and after collision. In other words, when you look at conservation of momentum, all what we are saying is that momentum before any collision is and must be the same as the momentum after the collision. So that is true if we don't have any other external forces that are acting on the system that do not disturb the system in all these other directions. For example, if we have no external force, it means that, for example, if we have particle 1, 2, and we have particle 2, 1, it means that what we have is that when two particles actually come together and collide, what we realize is that if, for example, there are situations where two particles will collide, then they move together, or they collide and they go in different directions. These two situations still actually obey the conservation of momentum, as long as there are no any other external forces that actually act on the system. So we have said that momentum is nothing but mv. So in the form of vector quantities that you've done in the first topic, We have also momentum can also be resolved in the XY plane and Z plane, of course. So what we are saying is that momentum in the X direction is nothing but the mass of that body multiplied by the velocity in that same direction. This applies to the Y-axis. Let's look at an example. We are saying an astronaut of mass 80 kgs pushes away from a space station by throwing a 0.75 kg wrench, which moves with a velocity of 24 meters per second relative to the original frame of the astronaut. What is the astronaut's recoil speed? So here we know very well that we have the mass. From our data, we know that we've been given the mass, which is 80 kgs. This is the mass of this guy, the astronaut, who is throwing something there. Then we are saying that it pushes away from a space station by throwing a 0.7 kg wrench, which is the one you are seeing on the picture that is thrown, this wrench, which is 0.75. Then which moves with a speed, that is the velocity of this wrench is actually 24 meters per second. So how do we come up with the recoil speed? I think this, you understand more of the recoil speed. Of course, you've looked at it in high school, but next semester when we'll be looking at, next semester when we'll be looking at some of the applications of these theories that you are doing now, you understand more on how this has an impact. For example, someone holding a gun and is shooting, you realize that when you're shooting, the bullet is going in front, then the person who is holding the gun also tends to be moving behind. And this is what we are calling the recoil speed. So the recoil speed is that speed which is, due to it's like a momentum of some kind. So you've thrown something and then you tend to be going backwards. So of course, this can be calculated from looking at the momentum of this range. The momentum we have said is mass multiplied by velocity. So the simplest way to calculate it is you have the 0.75, which is the mass, multiplied by its velocity, which is 24. Then you found the momentum of the system that goes away, which is the system that involves the range. Now, on the other hand, we have the astronaut who is 80 kgs. But what we don't know is his velocity, which we are calling the recoil speed. So in other words, we know that momentum before collision is equal to momentum after collisions. We have talked about conservation of momentum. So what you do here now, you have to get that momentum which you get from 0.75 multiplied by 24 is the momentum of the range. That you have to equate it now to mv, where m now is the mass of the astronaut, and then you have the velocity. So you make v the subject of the formula, and straight away you realize that your answer comes to 0.225 meters per second, which I've put down there in red. All right. I wanted to also reintroduce something which is not really relevant, but it's just for information. There's what is called the center of mass. For some of you who are going to get into the physics at second year, you understand how important this center of mass is. The center of mass, of course, of a body is where its weight is actually centered. So the center of mass actually does not accelerate. So that is just for your information to understand. In terms of momentum, the center of mass does not accelerate. This is with reference to the frame in which you are working on, which is just the center of mass frame. So these formulas which I've put here should not even, make you uncomfortable. They are just there to actually prove that this center of mass, which is nothing but the total momentum of all the particles that you have in the system, we divide by the total mass. So you realize that actually when you do that calculation at the far end, we actually see that the center of mass, the change in center of mass, which is xcm, is actually 0. So this is true if total momentum is equal to 0. All right. So we look at the next example, which of course I'll have to just try to explain to make you give you some hints, but you can still go through the details of the calculations. The answers, I've already put them there in red. Those are the solutions. So the second example says Ted and his ice boat combined mass. So you have first to understand the question. Every time you look at any question that you are trying to answer, whether in a test, whether you are studying, whether you are in an exam, the first and very important thing is to put yourself inside that question and understand what is the question trying to imply. So Ted and his ice boat. So here in brackets, the question says combined mass. So Ted together with the ice boat, their mass is at 240 kgs. They rest on a frictionless surface. You underline that word frictionless because this entails that there will be no friction between the boat and the surface of a frozen lake. A heavy rope. This rope has mass 80 kgs and length of 100 meters, is laid out in a line along the top of the lake. Initially, Ted and the rope are at rest. At time t equals 0, Ted turns on a winch, which winds 0.5 meters of rope into the boat every second. Then the first part of the question is asking you to say, what is Ted's velocity just after the wrench turns on? So what you need to understand here is you have two systems. There is the system where you have the boat, that is the system A, you have the boat and Ted is inside that boat. The second system is where you have the wrench, which is about 100 meters away and it's weighing 80 kgs. So this system B gives you the mass. So the distance from where the boat is to where the wrench is, it's about 100 meters. But that mass, that rope weighs 80 kgs. So momentum on the other system is mass multiplied by its velocity. Then momentum on this other system is actually the mass, which is 240 multiplied by the velocity at which these people move. So we are saying Ted turns on a wrench which winds 0.5 meters of rope onto the boat every second. So the tricky part of the question is just on the last sentence, which says 0.5 meters of the rope into the boat every second. This means this is relative to the speed at which the boat will be moving. So when you find the momentum of the boat, which is 240 multiplied by 0.5, then also you equate it to the mass of the rope, then multiplied by V2, which we don't know. And straight away you make V2 the subject of the formula and you get part A, which is 0.125 meters per second. Then we are saying what is the velocity of the rope at the same time. So this velocity of the rope, one thing that we need to understand is that the rope is reducing in terms of size. That's why first thing first, you need to understand that the velocity will have to be negative. So the moment you get the velocity of the wrench, then you need now to understand to say what is the velocity of the rope at the same time. So we are saying what is Ted's velocity just after the winch turns on. So that is the velocity. Now, from the next one, now you need to compare on the other side to say the momentum of the system A and the momentum of the system B should be equal. And when you equate the two, you realize that The other one should give you, that negative you see is nothing but showing that actually the velocity is the negative direction. Why? Because the rope is actually reducing in size. So as you go down, the next one is what is stage speed just as the rope finishes. When the rope finishes, what happens? There is no movement. So there's nothing to think about there, just put it here. The rope has finished, the boat has reached its destination, and there is no more movement. How far did the center of mass of tailed boat rope move? We know from our previous explanation that the center of mass does not move. Straight away you put a 0. How far did tail move? How far means the distance that has been covered. So how do you calculate the distance? You have the velocity, you have the momentum that you've been given. So straight away, you can actually deduce using one of the simple equations that you have for the 4 equations that you had in high school of motion. You can actually use one of the simplest, which is the last 2. You pick on the last 2, which are the equations of displacement. Then you can just plug in those values using answers from D, where you're using answers from C, where you know that the final velocity is 0, also knowing that the center of mass is equal to 0. When you plug in that formula and you know your momentum, you know your velocity, you know your acceleration, now what you don't know is the displacement. Straight away you come to 12.5 meters. How far did the center of mass of the rope move? Of course, the center of the mass of the rope was moving in the negative direction. In other words, you are being asked what amount of rope was tied onto the boat before the boat came out of the ice and got on the shore. This is what is being asked here. That's why you see that negative 37.5 there. How do you arrive at that minus 35? Is to look at the speed, also using part A and B to fuse in the formula of momentum, so that you are able now to determine how much of that 100 meters of the rope was tied on the boat before the boat reached the shore. All right, so that is a straight away example 3. I'll leave it and I'll skip it. It's very simple and straight away. You just need to use the formula M1 V1 is equal to M2 V2. Why am I saying so? You know that the system 1, you have the velocity, you have you have the mass, which is 3250 kgs. Also, you've been given the first mass is 1450 kgs. The second mass is the 3250 kgs. You have V1, which is 44.7 meters per second. You've just been asked to find V2. Straight away make V2 the subject of the formula, and you realize that you have 13.8 meters per second. Let's look at the next. We've talked about momentum, which we have actually identified to say momentum. We've defined it as mass multiplied by the velocity. So in other words, when you talk about momentum, the first thing that should tick in your mind is that momentum before collision must be the same as momentum after collision. Generally, this is how you actually solve most of the questions on momentum, be it in a test, be it in an exam. These are the basics of momentum. Let's look at what is called impulse. So we've talked about momentum to be equal to the mv. So if in a system there is change in momentum, then that change in momentum is what is called impulse. As simple as that. How do you define impulse? Impulse is defined as the change in momentum, full stop, where impulse is equal to change in momentum. We know that F is equal to change in momentum over change in T. That means F change in T is the same as the impulse. Now, looking at the diagrams, we are talking about the constant, For non-constant F, impulse is just the same as the area under F versus the curve. So if you have been given a curve like this one, and then you've been asked to say you find the impulse. In other words, what we are trying to say is you should calculate the area under the curve. As simple as that. Okay, let's look at the example on impulse. We have been given to say this picture throws a 0.145, excuse me, kgs baseball so that it crosses home plate horizontally with a speed of 40 meters per second. It is hit straight back at the pitcher with a final speed of 50 meters per second. The first part of the question is asking you to say, what is the impulse delivered by the ball? I've mentioned in the definition that impulse is nothing but the change in the momentum. So we know that the first thing first, we have to collect our data. We know the mass, we've been given the mass, we know the horizontal speed, and then we have been told that it is hit straight back at the pitcher with a final velocity of 50. So we now need to find, from here, we need to calculate, we have momentum before and momentum after. So what are we trying to say? We have the 0.145 kgs. So this we have to multiply it by 40. Then now we need to also multiply, we have M1 V1 is equal to M2 V2. So we have the M1, we have the V1, we don't have the M2, we have the V2. So when you do the calculations, the difference in the two momenta is what gives you the impulse. So straight away you realize that when you get the change in the momentum, you come to 13.05. So part B is talking about find the average force exerted by the bat on the ball if the two are in contact for 2.0 times 10 to the minus 3 seconds. Find the average force. We know that force is nothing but mass multiplied by acceleration. So our work here is to find the acceleration. And we know that the acceleration is the change in velocity over the change in time. So we have the changes in velocities, which is between 40 and 50. Then we have the time that we have been given here. So straight away we calculate the acceleration. Then we multiply it to the mass and we get 6,525 newtons. The last one is what is the acceleration experienced by the ball? Of course, acceleration is nothing but the change in velocity over the change in time. So this change in time, when we divide it up there, what we realize is that we have 45,000 meters per second squared. Let's look at some few definitions and some few terms that we have to pay particular attention when it comes to collisions. The first thing that we want to mention and to state categorically is that momentum is always conserved in a collision. So whether two bodies collide and then they actually move in separate directions, or they collide and then they move in the same direction, this doesn't matter. What we are saying is that momentum is always conserved. So there is what is called classification of collisions. We have what is called elastic. In elastic collisions, we have both energy and momentum being conserved. What are we trying to say? The momentum before the collision must be the same as the momentum after the collision. Then also energy. Energy before the collision must be the same as energy after the collision. But in a situation where we have inelastic collisions, what we see is that only momentum is conserved, but energy is not conserved. So here in in perfectly inelastic, this is where we have two bodies stick to each other. So lost energy goes to heat because of this sticking. Because when bodies stick to each other, they produce some kind of friction between them. And that friction creates heat. And that heat is lost in form of energy. So in an event where you have two bodies, collide, and then they move uh, in different direction. Under normal circumstances, there is a very high likelihood that you have both energy and momentum conserved. But in a situation where two cars collide, then they move together out of the road, you find that energy is not conserved, but momentum is. All right. These are just some of the examples. You may be asked to say examples of perfectly inelastic collisions: catching a baseball, football tackle, cars colliding and sticking. These are what are called inelastic, where two will have to stick and then move in the same direction. So the examples of perfectly elastic collisions, of course, super ball bouncing, of course, electron scattering. This is where we actually conserve energy as well as momentum. All right. So there's that example, which I'll leave it for you to look at it. We have a super ball bounces off the floor. Of course, here is just multiple choice. A super ball is just an example of elastic, where we have both energy and momentum conserved. So A, the net momentum of the Earth plus super ball is conserved. The net momentum, the net energy of the Earth plus super ball is conserved. Both the net energy and the net momentum are conserved. Neither are conserved. So what you just need to understand is the super ball, is it inelastic or it is elastic collision? In this case, we know that super ball bouncing is actually elastic. So here we know that both momentum and energy are conserved. Then look for that in the answers and you are able to pick which one is the answer. So this is another example where the astronaut is floating in space, of course, catches a baseball. So we are saying momentum of the astronaut, baseball is conserved, mechanical energy of this is the same. So we have first to look at this example that we have been given. Is it elastic? Is it inelastic? So you realize that this is nothing, but it is inelastic from the examples that we have. So straight away you get to, it's the same, you get to the answer. It is the same with a proton scattering. Proton scattering, it is under electron scattering. So straight away you know that it is elastic and you need to get the answer from there. So in perfect inelastic collision in one dimension, what we know is that mv plus m1 v1 plus M2 V2 will be the same as M1 plus M2, then V final, where V1 is initial, V2 is also initial, V final. Why have we factorized V final? Because these two bodies will actually stick. So their total mass will be M1 plus M2, but they will move at the same velocity. That's why we've put it as the VF, where I've put in red there to say final velocities are actually the same in elastic collisions. So that is a simple example that has been given there. And of course, the answers, I've given those two answers down there. We are saying we have been given the mass, which is 2665 kgs. Then we've been given the speed, which is 35 meters per hour. So we are saying this actually smashes into, 1061 kgs, also moving at that speed, which is nothing but 15.64 meters per second in the opposite direction. The cars collide and stick. So this is where you pick your solution from. These cars collide and do what? They stick. So if cars stick, what are we trying to say? This is inelastic collision. where these cars, their momentum will be the same, but the energy will not be conserved. So we are saying, what is the final velocity of the two vehicles? We are just from saying V1, M1, V1 plus M2, V2 must be the same as M1 plus M2 multiplied by VF. Where now we've been asked to say, what is the final velocity of the two vehicles? So you just pick that formula, put your mass 1 of the first vehicle, put its velocity, put the mass 2, put its velocity, and put their combined mass, and then make VF the subject of the formula, and straight away you get your part A. Part B, what are the equivalent brake walls speeds for each vehicle? So we are saying, what are the equivalent brake walls speed for each vehicle? In other words, what we are trying to say is that the first vehicle, which is 5979 lb, which is just like 2665 kgs, is actually going at this speed, which is 35 meters per hour. Now, that is meters hour. So you have 1060, which is a Honda Civic, which is moving at 15.64. Now you are saying, what are the equivalent brake wall speeds for each vehicle? What does this mean, brake wall? What we are trying to say is you are trying now to differentiate the two vehicles in terms of how they are actually moving as they are approaching this collision. And then you are trying to find out how best in terms of the difference, in terms of their speed. So the first part, you realize that the first vehicle, which is nothing but 35 mph, this, of course, we expect a huge reduction in the speed. The other one is 15. So the other one, which is actually moving at 15, this other one is moving at a higher speed. So there is one which is going to increase in speed. There is one which is going to reduce in speed as a result of the collision. For example, if you have two vehicles that are moving at different speeds, when they collide, the vehicle that is at a higher speed will reduce in terms of speed. The vehicle that is at a lower speed will increase in terms of speed. This is what we are trying to call here as brake wall speeds. Okay, a proton, which is of course of mass, so that is the mass of the proton, which of course you've been taught from chemistry, elastically collides with the target proton, and then what we get is that if the final velocity of the projectile, which is the proton, is at that, and the target proton bounces forward, what are the final velocity of the projectile, the proton? So, of course, the final velocity of the projectile for the proton, straight away, you don't have to think this is 0. So we are saying the second one, the final velocity of the target of the proton. So we have the initial velocity, we have the final velocity. So in the same way, you use the same M1 V1 is equal to M1 V1 plus M1 plus M2 V2 is nothing but equal to the M1 V1 plus M2 V2. So in other words, we are saying this is elastic. This is elastic collisions. What we are saying is these two particles will move in two different projectiles, in two different directions, and they will have different speeds. So when you do the calculation and plug in all the data that we have here, you realize that you come to that solution which is down there. Okay, I think here we don't need to talk much about that. I've mentioned about it. That is conservation of energy. Energies we've used in our first lecture, we used the kinetic energy, which is half mv squared. So the kinetic energy of the first vehicle plus the kinetic energy of the second vehicle or a body when you add them, must be equal to their kinetic energies after the collision. Conservation of momentum, momentum before collision must be equal to momentum after collision. I think that is straight away. Okay, I've talked about this already. Of course, that example you may go through it. It's just the same example as the one that we are just from looking at. So this, we've been given the mass of the proton. Of course, when you talk about the proton, the first thing that should ring a bell is that here we are looking at elastic collision. And in elastic collision, there are two things that define it. The first one is that the momentum is conserved. The second one is that the energy is also conserved. So initially, first thing, you have to use equation number 1 and also equation number 2 will have to be used. Then you are able now to solve that. So we'll end here for now. It's just that unfortunately, these videos were not actually stored on my YouTube. So it's really unfortunate. I had to redo them again. I thought that they were already there and you people had access to them. All right. Thank you so much. Have a good day.